All right, so today will be the last class before the reading week, and I think after today we will get enough materials for you to really go over during the reading week. So of course, after the reading week, we still get a few more weeks before your first written test, well, the only written test that's coming. So please check the calendar. Your assignment number 1 will be due, I believe, sometime next week. So please make sure finish it in time, or if not possible, well, try to finish early if possible. And then tutorial number 6 tomorrow, I will still host it. I haven't really decided yet exactly what to do, but very likely we can do some exercises on that first search. But we're definitely gonna do something very exciting today. Well, I'm quite excited too, right? We'll do it. Okay. Okay. Any questions about anything? Diego.
Just to clarify the topic last class that was sending about the number of spanning trees that you can get.
Yeah.
So the number we reached in class.
Yeah, the number.
It doesn't
Yeah, exactly. Yeah, you can still refer to the e-class announcement, please. Okay, very short, since you are asking. So the 56 that we use the choose operator, we choose, you can think about that's the number of spanning trees we can get by given the number of edges, right? Just choosing that. However, for quite many of them, they simply wouldn't qualify as a spanning tree because they might have a cycle, they have a disconnectiveness, etc. Okay.
Okay. And then to know the exact number.
The exact number is beyond the scope. I did mention some name over there, but we don't need to bother for this course. That'll be too complicated. All right, good. All right. Okay, good. Let's do a very quick recap, and then I do want to just summarize about a number of the edges for that first search, and then we'll talk about more complicated stuff today, okay? You guys have to get ready to take notes and draw today. It's going to be very heavy, okay? But, we'll see. So last time we kind of went over some summary table, so please make sure you really understand about the progression we have for the terms, about different graphs, right? The table here. And also some exercises, either visual or maybe I can convert it into maybe some like tuples, right? Because each graph can be specified as a tuple. Okay. And then we got properties for the graph, right? Something can be, if that's true, prove it by mathematical induction. If that's not true, you have to give a witness for showing violation. And we talk about traversal. What we did on Monday was about a basic undirected graph. So most likely tomorrow in the tutorial, we can go over another more complicated example together, right? So since we got a luxury of time doing the tutorial, it's really to make it interactive and also really make sure you can really do it. Today, I do want to go on to talk about the advanced case. That's something I really want to go through today, so you can try to struggle through a little bit over that over the reading week. So I'm going to talk about something mathematical about this particular search after the reading week. And breadth first search will come at some point very soon. And application, we'll get to it after the reading week. So that first search, the introductory example we did was if the graph we are trying to apply the DFS itself is a tree. In that case, it will simply correspond to a pre-order traversal, right? It's a special case. That means we got discovery edges only. There's no back edge because as soon as you have back edge, in the case of undirected graph, you have a cycle, right? So also make sure you know how to use a stack. And then that's the example we did from scratch last time, right? We did one example here and also did another one here. And tomorrow we can do one more. That's maybe even more complicated, right? That's something we can definitely practice together. Any questions about that first search in general? All good? Okay. I would like to just start today, C and D, you can do exercises. I want to just revisit very quickly about the edges that we have in undirected graph. Notice that it's very important whenever we talk about that first search. When you do it on the undirected graph, there are only two kinds of edges, discovery edges and also back edges. Okay, it's only these two, right? So this is like a screenshot from your slides, right? You can definitely take a look when you study for the lecture. So I just want to highlight when we talk about discovery edge versus the back edge, right? So these two are the things you want to pay attention to. And especially you will see something here. Ancestor. The ancestor and also accordingly descendants is really corresponding to when we revisit, when we review the balancing binary search tree. We talk about ancestor, we talk about descendants, right, for nodes. Exactly here. Because every time you try to do a DFS application or run, it's going to give you a DFS tree. That's what something that's so-called DFS tree. We'll see that again today. So since it's a tree, you can always talk about relative to a node, what would be its ancestor and descendants. That's something we have to pay attention to today, especially once we move on to the vector graph for DFS. Okay? So let's now just summarize about the kinds of edges. So before you actually get your DFS starting, so for undirected, I simply just say pink, right? Doesn't really matter. So you can, once we talk about the directed graph, you can follow that color convention if you want to. But for this one, just only for undirected. Okay? You can think about initially, all the vertices are unvisited. All vertices unvisited. And also all the edges unmarked. Okay? They're simply untouched. That's the beginning stage. It'll be very similar when we talk about directed graph, very similar. Okay? And whenever you want to start with a DFS, you should always pick the starting point, the starting vertex, which can be arbitrary. As long as the vertex itself is unvisited, that'll be okay. So let's say in this case, we're going to start from maybe A over here. Okay? And for another way, another diagram, I also start with A. Right? Discovery edge is really for you to go from one node that will lead you to another unvisited node. So for example, let's say we start with this initial configuration where everything is unvisited. What I do is I start with A right here. So that means A is visited right away, right? That's what we did last time. So I can directly try to, I can just try to change the color of this. Let me just do that over here. Okay, I can now change A to be a visited node, which will be green. And then from A here, I can either go to B or D or E. But our assumption is we do alphabetic order for the visiting. Okay? And then we're just going to mark this edge as a discovery edge. As soon as we do that, we're also going to change the color of the visited node. So B here is also going to become visited. Right? You can think about this single step shows you about discovery edge. You're just basically discovering something that has not been visited. There's another name for that. It's called discovery edge. Also, people also like to call it tree edge. That's also mentioned in your slides. Tree edge in the sense that all the discovery edges all together, they're going to form a tree, spanning tree, a DFS tree. That's why it's called tree edge as well. Right? So for example, if you look at that from last time, if you try to consider all the discovery edges we have done, you can see all of them form a tree, which will be all the vertices over here, and also just the tree edges is a tree. Okay. All right, so that's about discovery edge, and let's talk about back edge. Okay, let's understand this one, very important. Okay, let's bring the help from the stack. So what we do is, let's now think about a stack right here. So first of all, what we do is, I'm going to just visit several nodes at one go. Let's say I visit A already, and also B, and then also C. So the way I do it is by using two discovery edges, A to B, B to C. So far we're good. And then up to this point, how should the stack look like? It's going to be It's going to be A, and then B, and then C. All right, so far so good? Think about we are really building a tree when we are doing the depth first search. The DFS tree we are building right now is like this. We start with A lead us to B, and then lead us to C. So far, right? So you can think about the way we're doing it is A to B, B to C, exactly like that. Okay? Now, when we try to visit C here, so from C here, at the top of the stack, we got choices. Either we can go to A, we can go to B, we can go to D. If we try to go to A has been visited already. We said that it's a back edge, meaning that we have a cycle right here. Okay, so this is a back edge. Let's now dive a little bit more into it. If you want to think about it, this edge over here is going from C to A. If you look at the tree itself, from C to A, so C is this edge over here from C to A is really going to C's ancestor. The edge CA brings C to its ancestor, A. So that means we have a cycle. Another way to see that would be, you can see here, C is right here, and then we are trying to bring it to some earlier vertex that is still there. It's still in the stack. You want to get very comfortable about viewing this graph over here so far as either the tree look or the stack look. These are very important when we talk about the depth search on directed graph today. Things will get more complicated. Guys, please, any question? So important to get this right. Diego, you look puzzled. Go ahead. No. You're fine. Okay. All right. What we're going to see today is whenever you're seeing that C is going back to some node that has been visited, we have to then decide, in the case of directed graph, the edge may not be back edge anymore. There might be another two categories. It might be a descendants. It might be something that's neither ancestor nor descendants. So these are the three possibilities we have to explore in the case of the directed graph. So that's why things will get complicated. Right? But this one here is just a summary about how you can understand about marking edges for undirected graph, which is quite straightforward. You just got to be very patient about using the stack to really track. Okay? Okay, let's now move on to the actual thing for today. I already updated the slide, so please make sure before you study that, make sure you download the latest version from today. Okay? It's going to be slide number 31 and 32. It's very condensed. I put all the necessary terms you should really know right here. Let me just enumerate all of them first, and then we got to build from scratch, and then we'll do one complete example together to make sure you're okay. This is very important because after the reading week, I'm going to take this example here and extrapolate it into some general mathematical properties about everything. Right? So it's so important for you to make sure you understand about all the terms. Okay? We're going to talk about what is a DFS run, like an execution. And then we'll talk about DFS tree. That's something already said, but we're going to make it more visual, just another example. And also star vertex, and also what will be the root of the DFS tree. We're going to see that. Also ancestor, proper ancestor, descendants, and proper descendants. So these are all the important terms for you to also identify, right, when you're doing a particular DFS example. And now for vertex, right? So now we're going to follow the standard notation, okay? Each vertex can have up to 3 colors in their lifetime, starting with white, and then gray, and then black. All right? But we'll see, exactly. So each color has some specific meaning. You cannot just arbitrarily color that, right? So the mathematical property we're going to talk about after the reading week also depends on the color of the vertex, okay? Can be white, can be gray, and can be black. Okay? So I also put some narrative there just to explain what each color should really represent. But that's something I will say anyway in the example. So you can read it when you study. So that's about the colors. The next slide, we'll talk about timestamp. So this will be the trickiest bit. Okay? So remember, I try to label the edges as I try to do the depth search when we do the undirected graph, right, on Monday. So now we're going to make it more complete. Every time when we try to push or pop a vertex into or out of the stack, we have to somehow have some global timer starting from 1 and then try to gradually increment the counter and see at what timing are we really trying to push or pop a particular vertex into or out of the stack. And based on the values for the timers, we can also derive some very interesting mathematical properties. Right? That's something we'll see. Right? So there are two timestamps. For every vertex, you basically talk about something called discovery time. Just use a lower d. Okay, we'll get there. And also we got something called finish time. So D and F for every vertex. Okay. And of course, the finish time should be strictly larger than discovery time. That makes sense, right? You should always start before you can finish. All right, so here comes the complication. Now for edges, we're going to have 4 different categories. So we still have discovery edge, and the meaning is just the same as before. We're discovering unvisited vertices, discovery edges. And all the discovery edges in a single DFS run is going to form a DFS tree, spanning tree. Okay? And then we're going to, okay, you can look at the different definition there, but we're going to look at that by example. There will be something called discovery or tree edge, also back edge, forward edge, and cross edge. So these are all the 4 we're going to see today. All right? All right. All right, so these are about like a very quick overview about what we're going to do today. Okay, let's now get on to it. Before we even do the example, I would suggest we try to build up all the definition. I want you to really have the intuition about them. Okay, let's do that. This graph over here should look very familiar to you. If you recall, the graph that we did on Monday, right, is exactly this shape. Topology is the same. However, I just added some direction to each edge, just make it a directed graph. However, the way we're going to do the depth of search, the way we're going to trace it is going to be much more sophisticated once the directions has been incorporated to the example. All right. Okay, let's now do some notation. Let's start with, so important to clarify what's a DFS run. So DFS run. Or you can think about execution, a single. So whenever I say DFS run, I really say a single execution or application of the depth of search algorithm, a single one. A single execution or application of DFS. You know what, let me keep things a bit simpler. Why don't we say just, let me just say run, because I only mentioned run in the slides. I think that'll be better, okay? So whenever I talk about run, it's only a particular execution. And every time, in order for you to start a particular execution or application, you have to make sure you got some designated start vertex. For example, I might say you want to start from here, or maybe you can start from C, or you can start from E, etc. Right? It's possible. Okay? So each one of them has a designated start vertex. And of course, it is important to note the start vertex must be unvisited. Right? You start from there, unvisited. And a little bit look ahead. It's going to be a white vertex. Oh, bear with me. I'm going to talk about the colors at the end. And what will be the result? The result is going to be a so-called DFS tree, depth of search tree. Okay, tree, right here. And for this example here, okay, let's now, even before we try to trace it step by step, okay, let me just highlight the edges first, and that will just to give you the overall picture, okay? Let's say for this particular one, if I try to do my depth of search from A, let's say, that'll be the start vertex. It's also going to be the root of the DFS tree, okay? So this will be the start vertex of the DFS run. At the same time, it will be the root of the DFS tree. Okay, let's now just color that. At the end, every node will be visited. So they will all become black, all of them. Oh, I'm so sorry. There we go. At the end of the day, when the DFS terminates, all the reachable vertices will be just black, all visited, okay? But I'm going to show you exactly the progression for the color. For now, just think about it as a final screenshot, snapshot, okay? And turns out for this particular one, we're going to have discovery edge here, and also here, also here, and also here. 1, 2, 3, 4, which is exactly 1, 2, 3, 4, 5 minus 1. Again, that's a property we learned earlier. So it's a spanning tree, and it's a DFS tree. So DFS tree we have right away, we can do that. It's going to be here. So it's actually A as the root. And then it goes to B, goes to C, and goes to D. And then we also got 1 here. Right? It's our DFS tree. Okay? I'm going to use this tree here to also give you some visual correspondence very soon. Okay? So that's our DFS tree. What about these edges? If the graph was somehow undirected, we called all these edges just black edge. But in the case of directed graph, they have to be further categorized. Okay? Let's go over them one by one. So this one here, let's say, from A to C. Okay, A to C here. You can see that corresponding to the tree, what we're doing is we are basically going from A here to its descendants. It's called a back edge. So here, C is A's descendants. That's back edge. Another one here. I beg your pardon. I just said something wrong. Let me say it again. I really apologize. Okay, let me do it again. I meant to talk about another one. Okay, let me be careful. I should look at the wrong part of my notes. Okay, let me just undo this part. Okay, back edge will be this one here. Okay, this one here is so-called a back edge. Because if you look at the graph, we basically go from D to A. Whenever you're having a direction back to your descendant, back to your ancestor, it will be a back edge. That means you have a cycle already. All right. So A will be D's ancestor. It's a back edge. And the edge I just spoke about is so-called a forward edge. Right here. So this one here is called forward. We're basically going forward to your descendants. It's called forward edge. Okay, I'll put it here. It's called forward edge. If we try to see the correspondence, so basically go from A to C. When you go from A to C over here, you're basically going from A to one of its descendants. C here is A's descendants. Okay, that's forward. So backward and forward. Okay, there will be something a little bit more elaborate I need to talk about, but we'll get there once we do the tracing. Okay, and the final kind is here, from E to C. It's called a cross edge. It's basically saying you're going from one subtree into another subtree. So that means the node you're going to is neither your ancestor nor your descendants. But how do we see that? Okay, so you go from E to A. E here, E to C, beg your pardon, from E to C. You can see if we go from E to C over here, that direction there. Right, so that's the direction. So the C here C is neither E's ancestor nor descendants. So you can think about E here and C here, they belong to different subtrees under A. In that case, you're going from subtree to subtree. It's a cross edge. Okay? I want to give you some visual intro first. Don't worry, I'm going to repeat from different angle as we go. It's very complicated, but just take as much as you can. Okay. So we got 4 kinds of edges. We're going to do another summary before we do the tracing. So we got discovery edge, we got back edge, we got forward edge, we got cross edge. Okay? And then we talk about graph traversal. You might be, for example, given a graph that has more than one connected components. So that means intuitively one single depth first search run cannot really cover all the vertices and edges. That's one case. After the leading week, I'm gonna give you all the complete cases. But just intuitively think about if you got more than one connected components, you might need multiple DFS runs to cover that. Yes, question.
Is there any way to see the difference between a back and forward edge without looking at the DFS tree?
It's definitely a way. We're going to see exactly. So when we do the tracing, the way for you to really look at is to look at the color of the nodes and also the timestamp. We'll make it very algorithmic. But I think visually, that's also I want to show to you as well. Okay, good. Okay, graph traversal. If you actually want to traverse, visit all the vertices and also edges. Okay, so first of all, we go with each run. Each DFS run starts with a different vertex. You never repeat, because once the current DFS run is done, all the vertices have been visited, so you don't really choose them anymore. And in general, one or more DFS runs required to traverse the whole graph. Okay, one or more. And after reading week, we're going to discuss in detail about what more exactly should look like. But let's not worry just yet. Okay. So this part here is going to be discussed later. Today we're going to focus on a single DFS run will be sufficient. Okay. What will be the result? Think very logically. Every DFS run is going to give you a tree. If you got multiple DFS run, that will give you multiple trees. What's the term for a collection of trees? Forest, exactly, right? Good. It's going to be a DFS forest. Which will be just a collection of DFS trees. Okay, we'll see that a little bit more after the reading week. Okay. Let's also clarify very quickly about ancestor, proper ancestor, etc. Okay, I'll put it here. So we got ancestor, also proper ancestor, also descendants, also proper descendants. So the proper here is very similar to when we talk about proper subset. That means we are reducing strictly one element from there, right? It cannot be just equal, okay? But let's see. Let me say, how about this? What will be the ancestor of D? Right? You can either try to see the graph. If you go backwards, D itself, and then C, and then B, and then A. Or you can look at here, D, C, B, A. That might be more intuitive for you, right? That's something we did earlier. You also are doing it for your assignments, right? So ancestor would be D, C, B, and A, including D itself. Now, for proper ancestor, just excluding D itself. Of D. Basically, C and B and A. And very similar for descendants. Of course, you can say that the descendants of A here is going to be everything that's reachable from A, which it would be B, C, D, E, and A itself. That'll be descendants. But let's see another one. What will be the descendants of B, for example? Should be everything that's reachable from B, C and D, and also B itself. If you look at here, the descendants of B will be B itself, C, and D, nothing else. Right? So descendants of B, B itself, C, and D. Proper descendants will be excluding B itself, C, and D. Okay? Okay, two more things, and then we'll do tracing. Two more things. Okay? How about the color for the vertices? Colors of vertices. Right here. Okay? So typically, you will actually get each vertex is going to have a lifetime of three colors. Usually, it's going to be white, followed by gray, followed by black. Okay? So let's say we got one vertex here. Let's say it's the same vertex. Another vertex here. Okay? Another version. Let's say it's all X, X, and X. When we first start with, each vertex will just be white. And white simply means it has not been visited yet, and also it has not been pushed to the stack. Unvisited, also not in stack. As soon as we push X into the stack, because we have discovered that, we're going to turn that into gray. Gray simply means we have discovered that it's been visited. However, it has not backtracked just yet. There's still some outgoing edges that has not been visited just yet. Okay? You can see also the definition on the slides. So this one here, X, that'll be gray. It's being visited, not finished yet, still in the stack. Okay? There are many things you will see exactly when we try to trace. Okay? And finally, once you have explored all the outgoing edges for X, nothing else to go any further, X should be backtrack. It's finished. It's going to be right here. And that one there is what we call, that's the black color. That means the vertex is finished. And also, we can think about it's backtracked. And it should be popped from the stack. All right? Yeah, question? Oh, so in the case of a directed graph, we only care about outgoing edges because it can only go out from X by outgoing edges, right? For incoming edges, that's the problem for the other end, not for the X itself. Yeah. Okay, good. Let me say one more thing, okay? Color and timestamp. It's going to be some integer counter, starting from 0. Well, once we start counting, it's going to be from to 1, to 2, to 3, and etc. Right? Something you can compare. For every vertex, we're going to have 2 timestamp. For every vertex, let's say vertex x, d of x, and also f of x. Okay, for every vertex. Right? So d of x will tell you about the discovery time. Basically, what's the time when you push X onto the stack, when you first discover that? Okay. Intuitively, think about push time, but nobody said that, right? Intuitively, you can think about it. Okay. And then another one would be f of x. It will be the finish time. The timing at which you try to pop that particular vertex from the stack. Okay, finish time. Pop. Okay, there's a very important healthiness property that must be true, like a requirements. We can formulate it. Okay, basically, the timer for f for the same vertex must be strictly larger than its starting time. For example, if I start the vertex at 1, the finish time must be something larger than 1, right? So let me formulate a property right here, and then we can possibly take an earlier short break, and then we'll do the trace. The property is right here. For every x, x is a vertex, capital V. That implies the finish time of x must be strictly larger than the discovery time for x. That's very easy to understand. We can also very easy to see once we do the tracing table. But after the reading week, we have to somehow take this one here, the D and F. Try to think about what would be the relationship between D and F with all the vertices on the graph. That's something we're going to see after the reading week. All right. I kind of plan to do another page over here, but that one will be more like a repetition about what I already said. So I would suggest I can leave this page maybe just for recap after the reading week. Maybe that would be a nice way to maybe recap your study during the reading week. I can leave that, but I would suggest we take an earlier break today, almost there halfway. And then we're going to spend almost the rest of the class doing tracing. All right. Why don't we take attendance now and then take a break. All right, so let's now try to do tracing. This is a simple example, not many nodes, not many edges, but that one very nicely shows us all the 4 kinds of edges at the end. Very nice. But I think for the assignment, I'll give you something maybe more complicated so you can really practice. Right? I think that'll be enough preparation for just that part for the test. Okay? Let's set it up. There will be 4 things you have to keep track of at the same time. Let's set it up and then we'll do it. Okay? First of all, we can still do the push and pop as we did earlier for undirected graph. Right? Again, it's so important to actually qualify to say this is for directed graph. But it should be quite obvious because the input graph there is actually directed, right? Right. So the first table we're going to trace will be push and pop. We got 5 vertices already, 1, 2, 3, 4, 5. We can kind of anticipate we should get 1, 2, 3, 4, 5 for push, 1, 2, 3, 4, 5 for pop. Okay? At the end, at some point. Push and pop. Okay? And I want to also get 1 table for the timestamp. For every vertex, we're going to have the D and F. If you recall what we said earlier before the break, D here is the discovery time. And the F here is the finish time. All right, finish time. Discovery versus finish. And that should be the case for every vertex. So what I would do is we got 5 vertices in total. 1, 2, 3, 4, 5, yeah. Okay, let's have 5 rows. A, B, A, B, C, D, and E. And of course, we also have the stack itself. Right here. If you're doing this on a page, try to leave as much space as possible for here. It's going to be the main thing. Okay. So now another table. We're going to keep track about the colors for all the vertices. Okay? So because we know that there are 3 possible colors, white, gray, and black. So this is how I'm going to plan it out. Okay? I'm going to have a table starting from, let's say here. Okay? And I'll talk about the number of rows in just one moment. And then we got some timer. Okay? So T here is a global timer. The value of T is very important. We're going to use the T to really express some very nice mathematical property. But I'll do that after the reading week. Okay? So there are 3 colors. We got white. Also, we got gray. And also we got black. Now, the question is, how many rows should we have? It's something you can kind of anticipate beforehand. What I said before the break, basically every time you want to record a timer for each vertex is when it gets push or pop onto or from the stack. Every vertex may be push once, pop once. How many vertices do we have? 5. 2 times 5, 10. We've got 10 possible timer values we have to keep track. So that means 10 rows in this table. Okay? I'll write it down as well, but let's now draw 10 rows. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and it should be somehow 11 because initially 0. That's when that's when we haven't started anything yet. Okay, so let me just see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, that's good. That's good. So let me just make it a little bit better. There we go. Okay, leave some space over here. I'm going to write some insights here as well later. Okay. All right, let's now get started. And of course, the start vertex is going to be right here. We start from A. Again, it doesn't need to be. Okay? Any arbitrary, unvisited vertex will be okay. Before we even get started with the DFS, every vertex over here will just be white, right here. So that means we can simply numerate all the vertices that's white. All the vertices here will be white, right? All the vertices. So I'm going to put A, B, C, D, E. A, B, C, D, E. No, nothing gray and nothing black just yet. That's the initial setup. Okay, and the timer value right now is just 0. Okay, so we'll start with this one here. So A here is now being discovered, which will turn from white to gray. Okay, it's going to turn from white to gray. Okay, so that means over here, we're going to get one gray vertex, which will be A. And then everything else will be still white. And then we're going to push A to the stack. Push A to the stack. Now let's record a timer. Used to be 0 plus 1 is now going to be 1 for the discovery of A. So 1 here. All right. So what we have done so far is when we actually have discovered this vertex here, we increment the counter for the global timer. So now it's timing number 1, time unit 1. And then at time unit 1, we actually got A pushed to the stack. and then it turns to the color gray. Okay? So that's good. You can see that when you actually have the discovery time something but finish time undefined, that means the vertex is still on the stack. That's something you will see as well. There are so many things you can observe as well when you do the example. Okay? All right, so now let's do the next one. And how many choices do we have? Now, given as directed, we can either go for this way, go this way, or this way, right? Not this way, because that's this direction, right? So we got 3 possible outgoing edges from A, and we're still making the same assumption, alphabetic order. Okay? So what we do is we're going to have a discovery edge right here. And that's the very first edge we have to mark. I'll put 1 here. Okay? What this will do is it's going to discover B right here, right? As soon as we discover B, we're actually going to turn the color of B into gray right here, right? And then we're actually going to increment the counter of the global timer from 1 to 2. Okay? So now we have C, D, and E. For the gray, we actually got A and B. Okay? I'll also try to maybe circle this. So you can see that when we actually go from this row to this row, A is changed. When you actually go from this row to this row, B was changed. Okay? Just some additional information for you to see. Okay? So, of course, we're going to push B to the stack and B to the stack. And for the discovery time for B, it's going to be 2. So far we have done 2 examples for discovery edges. Every time you got a discovery edge, you got to increment the counter, basically, right? Well, actually, you never decrement the counter. So either when you will see, either when you push will pop. I think that might be more accurate to say that. All right, so we are now in B. We only got 1 choice going forward, right? Another discovery edge right here. Okay, this will be the second edge that we are doing. And this one here is going to discover C. And C is now going to turn from white to gray, again, as before. Okay? So that means we're going to push C to the stack. Increment the counter from 2 to 3, and C has been turned into gray. So now we got A, B, and C. And of course, so also good? Okay. Oh, by the way, there's something you can already kind of observe. The tree we are trying to build so far is like A, I'll do that. A here, and then B here, and then C here. If you look at the discovery time, descendants discovery time must be strictly larger than ancestor discovery time. Obvious, right? Okay? That's something we'll also summarize after the reading week, but that's something you can already pick up. Okay, next one. From C over here, we have only 1 choice, go to D. But still discovery. That's okay, we're getting there. Okay? Still just 1. So we're going to go for another discovery edge. So that one is going to be number 3, which will trigger D to be pushed to the stack. And we're going to increment the counter from 3 to 4, the timer. And then D will turn to gray. That means we got only E left. That's actually white, which means only E is unvisited. And then we got A, B, C, D. And of course, the timer for D will be 4 for discovery. Another thing to note, you can see that the gray color vertices correspond to exactly what's currently on the stack. Right? White color simply means it's not even pushed to the stack. Black color means it's being already popped from the stack and never pushed back. Gray means it's now just in the stack to be handled. As soon as all its outgoing edges have been handled, it's going to be popped and backtracked. Okay, that's something you want to keep in mind as well. Okay. All right, next. So now we are here, D. Well, only one choice, right here. All right, let's now write it down first. This one here is going to be right here. Okay, so this will be number 4. This is some edge that's going to be either back, forward, or back. Either back or forward or cross edge, which is not going to trigger any push or pop. So that means the timer shouldn't change. So we shouldn't need to update this table for this one here. Okay, just number 1. Number 2, what kind of edge is that? Let's now try to see that. Okay. So what we're doing is we're trying to go from D to A. Okay? We're trying to go from D here to A. The fact that discovery time here is strictly smaller than that. We know that A is an ancestor of D. So this is an edge that's really leading from this into an ancestor. So it's called a back edge. Okay? And I will also record at this moment is now timing number 4. We are doing this observation when t is equal to 4, right? Exactly this timing. When t is equal to 4. And I'm going to say a little bit more. Okay? Back edge. Okay, I'll set it here. So we got the edge DA. This edge right here. Handled when t is equal to 4. Right now here. Right? And it's considered a back edge. Because D of A is strictly smaller than the D of D. A is ancestor. Back edge by definition. And also notice that at this point, A is not finished. It's not possible A would have been finished because your ancestor will finish definitely later than you are. The last in, first out nature. Ancestors always finish before, always finish after descendants. Right? That's something we'll try to also formulate later. Okay? That's the last in, first out nature of the stack. Guys, any questions so far? Okay, we're good, right? We still got a little bit more to go, right? Only got 7 edges, right? But we're still not quite there yet. Okay? All right, next. So now for D here, anything else we should do? Not quite, right? Because you can see the only edge going out has been handled, has been identified as a back edge. So D here has no other things to do. Finished. Right? So that means we're going to let D backtrack. So what we do is we're going to increment the counter over here from 4 to 5. And now we're going to change the color of D. Okay? So what I would do is I'm going to overlay the color. Okay? So you can just think about it used to be gray, but it has now become black. Okay? So what I would do is I'm just going to put something like this. Okay? It's not become black. So that means it should be popped from the stack. So D should be popped from the stack right here. And we should really record this time over here as the finish time for D. So for D here, the finish time is 5. Notice that it makes sense. 5 larger than 4, right? All right. And of course, after this, what's going to happen? So we still got E on Explorer still white, but now D is no longer gray. So yeah, D is no longer gray. So A, B, and C, and D has now become black. Right here. All right. We're halfway. Okay. All right, so after this, you can see now on the top of the stack, we got C. Anything for us to do for C? Not really, right? You can see the only outgoing edges for C will be here. We handled that already, nothing else. So time to backtrack C. All right, so what we do is we're going to remove C from the stack. And we're going to increment the counter. 6. So that means A and B, and then we got D and C. And C, was, of course, was the change. And then we're going to make the color different. C here is going to become black. Good? All right. And then the next step, the top of the stack is B. B has only one outgoing edge. That one has been handled already. Backtrack, right? Similar. So we're going to increment the counter to 7. And then E here, and then A, D, C, and B. So B is the one that's being turned into black. Also pop from the stack. Okay? So you can think about D, C, and B here, and B is pop off. Okay? And then for B, it's going to be 7. Right? Finish time. Oh, there's something I forgot to really fill it in. So remember when we actually got this timer 6, we actually removed C. So C should be 6. Just be careful. Always remember to put in the information. Okay? Another interesting fact, you can see that. If you look at the finish time, 5, 6, and 7, D, C, B. The pop order, D, C, B. Right? They really correspond to each other. Okay? So after B is being popped off, so now we are A, right here. So what should we do? Well, this one has been handled, so the next one we either go to C or go to E, alphabetic order. So go to C. But the problem is C here is not white. It cannot be a discovery edge. It's got to be either back, cross, or forward. Okay? So now this will be another case we got to look at carefully. This one here, right here, is going to be number 5. Okay? Number 4 was a back edge. Okay? Number 5 here is going to be so-called a forward edge. Now we can talk about it. Let's simply. So at this point, we don't really, we don't really increment the counter because we haven't really pushed or popped anything. Right? The counter remains the same. But we should really take a look at exactly what A to C really get reflected to what we have traced so far. So from A to C. So from A to C, A here, And then to C over here, you can see the direction goes this way. At this point, you can see that C has already finished. Right? So now what we can say is this is something called a forward edge. I'm going to write some detail to you. It's called a forward edge. And at this point, we are now in time 7. Okay? So this is called a forward edge. Okay, double star. Okay, let's talk about this one. Okay? So this one here, AC. AC handled when the timer is exactly 7 right now. At this point, when we go from A to C, first of all, you can see that we are going to a descendance because the discovery time of C is strictly larger than the discovery time of A. Right? So C is a descendance. At the same time, C is already finished. By definition, if the edge is leading to a descendant that's already black or finished, it's a forward edge. Okay. Forward edge. Because the discovery of C is strictly larger than the discovery of A. So that is to say, C over here is a finished descendants. Finished descendants. Of course, when you say A is ancestor, you can say A is unfinished ancestor if you want to. Okay, it is unfinished. All right. Try to really focus on also how we use a timestamp to also justify. That's something we're going to make it general after the reading week. But I think by this example here is a very nice one to really show you every little detail. Right? We're just going to generalize it. Okay. All right. Next. So we are still in A here. And then A here, we have handled this, we have handled that. The next one will be E. What should this be? Okay, go. Okay, so let's do the previews. I think we have done enough, so you guys can tell me a little bit about how to continue. Let's run it, dry run. If I want to handle A to E, what should I do? Increment counter, I agree, because we want to push or pop. We want to push E, yes. So that should be what kind of edge? Discovery. Very good, thank you. Awesome. All right, so what we do is we're now discovering E right here. Okay, so this will be number 6. And then we're going to push E to the stack, meaning that we have to increment the counter right here. So that means all the vertices are not white because all of them have been visited. So now we're going to get A and E being gray, meaning that A and E are still on the stack. Right? So the E here is what we have changed. And the black vertices remain the same. All right, right here. And then, of course, we got to record this time. E here will be number 8. Right? Okay, we're getting there. Getting there. All right, so now E should be the top of the stack to handle. For E here, there's only one outgoing edge. This one's fun. All right? This one here cannot be discovery. Why? Because C here, not only that it has been visited, but also it's being already popped from the stack. It should not be bothered anymore. is finished. Right? Remember, we actually popped C earlier. Right? It's already finished. Okay? So this one here is a different category of the vertex, of the edge. Okay? This will be the final edge, number 7. This is what we call a cross edge. Okay, let's now record the timer, and then we'll see how to understand it. So what we have is from E to C. From E to C. Okay, from E to C. So this is so-called a cross edge. And we have identified this when the timer is exactly equal to 8. All right, that's a cross edge. So 1, 2, and 3. Okay. And notice that C here is also already finished. Okay. And more importantly, if you look at the tree we have so far, right? So you can think about what we have already was we got A here to B, and then to C, and then to D by discovery edges. And then we also branch out to E, right? So what we have is A, and then B, and then C, and then D. And now we are crossing out to E. Okay? From the tree over here, from E to C. So C here is neither is ancestor nor descendants. Okay, I can write it down here too. Okay. So what we're talking about is EC, handled when T is equal to 8. And this will be considered a cross edge. Because, number 1, the destination, C here, is already finished. It's already popped off on the stack. It's completely handled, already backtracked. At the same time, if you look at the tree structure over here, C is in a different subtree from the subtree that contains E. So it's a cross edge. I'll try to maybe answer your question, I know a little bit earlier, how we can see this algorithmically. That's something we can cover with more insight, maybe on the Monday when we return. Okay? Because C is a non-descendant and non-ancestor of A. Okay? But it's also finished. Okay? Also important to know that C is also already finished. Okay, good. All right, so far so good. All right, so what we should do is, so E here, when we first discover E, it's actually A here. Okay, good. So now for E, because we have already visited that, so it should turn gray in the previous one, right? So now, do we have any other choice for E? We already identified this edge over here. It's a cross edge, but nothing else. No more outgoing edges. So that means that one is going to turn black, okay, as well. Okay. So that means we're going to cross out E from the stack. And that will really correspond to, we're going to have E here being popped from the stack. And we got to increment the counter as before, number 9, A. So E is no longer gray. It's going to be D, C, B, and then E. And most importantly, we should really record the finish time. which will be 9. All right. Yeah, so early on, when I actually tried to pop B from the stack, I forgot to really turn this into black. That's my mistake. It should be turned into black, right? I just noticed that. Okay? So this is to say when B was actually removed from the stack, we should really turn it to be black. I just didn't do that when I was going over. Just make sure you do that at that particular step. Okay? So now the top of the stack is A. As far as A is concerned, all the outgoing edges have been handled. That means we should really backtrack on A. Okay? Let's do the final step. Okay, we're getting there. So that means A is going to be pop from the stack. Go away. And then we're going to have one more row, the last row. And then A will be now also become black. Right here. Okay? And then the time, let's record that, 10. All right, so that's a complete tracing. Okay? We've only got a few minutes. Let me maybe wrap up. I don't think I should really cover anything more. I think that this is something you really, really want to go over and practice over the weekend. Oh, sorry, not the weekend, the whole reading week. Maybe weekend is not enough. You really want to go over that. There are many things here. You can see just by tracing the push and pop, as we did for undirected graph, is no longer far from sufficient. If you only try to use these two, there's so much information you just simply cannot get. You really want to get to tracing the discovery and finish time, and also the different colors for the vertices. So these are the two things you really want to feel comfortable about tracing. So after the reading week, we're going to look at this example here. We're going to generalize some interesting mathematical properties about D and F. That's what we'll do. Okay? Guys, any questions? All right, just gotta practice and then go over that. I think I really did what I wanted to do. So I'll see you tomorrow, Thursday, in the tutorial. Okay, see you later.